Hello everyone, and welcome to the next lesson of School of Solana with Eki Blockchain. It's Adam here, and today we will be talking about security in Solana programs. So yeah, let's jump straight in. So first of all, I would like to start with the motivation and why should you care actually about the security. So as you all know, there is a lot of money in crypto space. And actually in 2022, there was over $4 billion that were lost in the crypto space overall. There was roughly over 500 million stolen on Solana ecosystem only. So I have done a little research here, and I found the biggest exploits on Solana last year. So maybe you might know, so there is a wormhole, so actually it's one of the biggest ever, where approximately $338 million were stolen or lost. Then there is Casio, $52 million, Crema Finance, $8 million, and also I have included here Mango Markets, where approximately $116 million in the time of exploit were lost. So yeah, I have included also Mango Markets, although someone might say that it wasn't a bug, it was a feature of the protocol, but never mind, you know, it was an exploit of the platform. So yeah, I think it's obvious why everybody should care about the security, because yeah, there is a lot of money in the crypto space, so we must secure the funds as much as we can. So here I have some basic security tips for you before we will start with the actual exploits. And the first tip is use Anchor in most cases. Why you should do that? So actually it saves you a lot of boilerplate code in the first hand, so you can basically focus on the business logic of your program, and you don't have to, you know, care so much about the correctly implementing all the checks. And I have included here a little example on the right side. So here this is a very short code on 35 lines, which is written in Anchor. So in Anchor, it's really short, and the instruction has, you know, only one line, whereas there is the context that contains most of the security checks. Yeah, so the code is very clean and easy to understand. Whereas if you use cargo expand command, so you can try it by yourself also on your programs, so you will see what Anchor actually generates and what kind of checks are there. And so this code, after some formatting, you know, expands to roughly 800 lines. So there are not only security checks, of course, there is some other boilerplate generated by Anchor, but it gives you an idea what actually Anchor does for you. Yeah, so this is one reason, and also Anchor, it became actually kind of standard in Solana, so it will be easier for everyone to review your code. If it's your colleagues or maybe some auditors, I would recommend you to use Anchor. So of course there are some situations where you might use raw Solana, no doubt, but yeah, especially if you are a beginner, I highly recommend you to use Anchor. Next tips. test extensively. So yeah, it is a problem in crypto space that the projects would like to deploy their projects very quickly. So the focus on testing is not so high. However, I would recommend you to test extensively and not only the happy path scenarios, but focus also on unhappy path scenarios. And there is a common saying, think like a hacker. Yeah. So you should really try to supply different inputs to your program, some uncommon or unexpected inputs, and so on. This might really uncover different bugs and security issues in the beginning of your project. And last but not least, have your project audited. So we all make mistakes, and as an example, there is a lot of programs directly from Solana Foundation. So you might think that these guys are the best in the field. It might be true, but still they get audits. So never trust only yourself. Get audited. Even the auditors are only human, so it's recommended to have at least 2 independent audits. And just do not trust only yourself. So yeah, these are the basic security tips, and now we can go to the common security exploits. There is a lot of different kinds of exploits. Maybe some of them could be grouped together because they have the same basis. I have chosen here some of them, the most important and the most common, and we will go through each of them. I will show you some examples, how it might be exploited, and what is actually the correct solution. The first one is signer check. So probably you already spoke about it in the previous lessons. It is very important that you verify that the right parties have signed a transaction. Here is an example of incorrect or insecure code. This is actually just the anchor context, which is called update user data. It is a context of an instruction of the same name. So imagine that a user would like to update some data on chain. And here you can see that one input account is the user account, and the other one is the data account. So the data account is bound to the user because it is a PDA address that is based on some seeds. It's the user data and the user key. However, here in this case of the user account, only account info type is used, and this type actually does not check anything. So it is insecure, and actually anyone who knows public key of the user can call this instruction. And he doesn't need to know the private key to sign it. So in that case, anyone can basically supply the correct user account and update the data of any user. So the correct way to do it with Anchor, instead of using account info, would be to use the signer type. The signer type actually automatically verifies that the signer or that this user signed the transaction, and therefore in this case you cannot supply a different user account for a given data account. The next vulnerability is the missing address check. So in that case you have to verify that an account has the expected address. So as you know, you are already familiar with the Solana programming model. So you know that each program needs as inputs all the accounts that it will work with. So it will that it will read or write to. In maybe not most cases, but very often you have to verify that the supplied accounts are actually the accounts that you expect. So here is again an example. Imagine you have some struct that holds configuration data. So the first is a public key of an admin that is allowed to modify some data and the data itself. Again, here we have the context of the instruction and with two accounts. So the first account is the admin account that has to sign the instruction, so that's correct. And the other account is a PDA account with the config data that is on some PDA address, global address for your program. So in this case, actually it is insecure because the admin account is not bound to the config account and to the data itself. So actually in your program you would like to verify that the admin account is the same account that is saved in your configuration data, and it is not done here. So what an attacker could easily do is to supply any kind of account as for admin, sign the transaction, and then supply the configuration data of your program, and the program would work. The correct way to do it is to use anchors constraint. So there are actually different ways how to implement it, but at least for me the nicest one is to use the has1 constraint. As here you can see, we have here has1 admin. So actually here the name admin has to match the data structure. So you have here the admin name in your config data, and it has to match also the name of the account that you supply. So it will verify that the admin account is actually the same or has the same public key as it is saved in your configuration data. That way you cannot supply different admin account. Then we have the owner check, or the ownership check. It is a little bit similar. So you have to check that an account that you supplied to your program is owned by the expected program. Here is a scheme. So you have your program here that receives as input some configuration data account, for example, and as you know, each account has different fields. So one of the fields is the owner field that holds the public key of the owner of your account, and then you have some data, for example. And if we will take this code. Again, it is a context of withdraw instruction, and consider following scenario. So again, we have an admin that signs the instruction. For now, for the purpose of this example, just let's suppose that the admin is verified directly in the instruction. So we omitted it here, so we can use the account info structure or type. So yeah, let's consider that we cannot supply a different admin, that it is checked elsewhere. It is possible. But for some reason we have decided to use an unchecked account info type for the configuration account, and then we have some treasury account that is again a PDA. So in that case, an attacker could actually create the configuration account by his program, and he could basically create exactly the same data structure of the config account. So when it is passed in your program, he will be able to access the config.admin.key property or function, and the check that the admin and the configuration saved in your account are same will pass, and therefore it will allow him, for example, to withdraw the fees from the treasury. So yeah, this is of course insecure, and the correct way to do it here is simply to use the account type. So the account type actually automatically checks the owner. So if you leave it just the way it is here on the right side, that it will then Anchor will expect that the owner of this account should be your program, and actually it will check it for you automatically. You don't have to do anything else here. In some cases you might want that the owner is some different program, for example, so in that case you can use the owner constraint. But yeah, it's actually very easy to do the ownership check with Anchor, and what I want to show here is that in most cases, if you have an account that you would like to deserialize, so a data account, then you will anyway use the account type, because then you have to also supply the type or the structure that you would like to deserialize. So it's not very likely that you would use the account info. So in that way, Anchor is quite intuitive. But anyway, I wanted to show you here the ownership exploit, so you might know that it may happen. And maybe another remark here. So for the treasury account, we actually used account info, but besides the fact that this is not the data account, it is just address that holds the funds. But here is also another owner check that is kind of intrinsic in the fact that the treasury account is on a PDA address. And if it is a PDA address, as you might already know, the PDA address is derived from some seeds. So in this case, this is the treasury here, the bump, and also the ID or the public key of your program. So actually Anchor here checks that the address is correct, because it will calculate and verify for you that the PDA address is correctly calculated here. So this is another way how you can check for ownership. So the next exploit is arbitrary CPI. CPI stands for cross-program invocation. So it's a little bit similar to the previous one in that way that you have to verify that the target program that we want to invoke has the correct address. So let's take a following structure of a program. Let's suppose that we have a main program, and this main program calls an external program and also takes as inputs the user account, some pool account, and also maybe some system account. I omitted it here for the sake of simplicity. And yeah, so the external program that you would like to call, of course, has some key that actually you have to verify. But yeah, before we will, I can show you how you can do it. I can give you an example how you can actually exploit the arbitrary CPI. So imagine the scenario that you have your main program that for some reason calls your external program in order to transfer the funds from the user account to the pool account. And so the main program calls the external program, and once the external program successfully finishes its execution, then the main program will log that the user, for example, deposited some amount to the pool account. And again, for some reason, it's only the external program that verifies the correctness of the pool account address. So the way how you could exploit it is that actually anyone, if you do not check the key of your external program and that it is the correct program that the main program should execute, is that you can supply a different program that will actually take the signature from the user. Yeah, so the external program, due to privilege propagation, will be allowed to transfer the fund from the user account. So it will transfer the fund to maybe some other account, or it will actually not transfer the account the funds at all. But the supplied malicious program will actually successfully finish, and then your main program will not notice that something bad happened, and it will log that the given user actually locked his funds in the pool account. So this is actually something that you don't want. And how actually it might see in your program, again, if you use the account info type, which is unchecked. And yeah, the correct way to do it is to use Anchor's program type. The program type verifies that the program, which is in that case called my program, has the correct address as you expect. There is a little remark to that. So Anchor actually supports out of the box only 3 programs. So the first program is system program, if you want to create, for example, new accounts, and then token and associated token. programs. So these are the the programs that are used very often. That's why Anchor supports them out of the box. Then, of course, you can use Anchor to basically generate for you the CPI modules automatically. It is out of scope of this lesson, but yeah, it's quite easy. So I would recommend you to check the cross-program invocations chapter in the Anchor's documentation. Yeah, but once you do that, then the verification of your external program is really very easy. You can only use the program type and the name of your program, and then again, Anchor does the checks for you. Then we have the math and logical issues. So this chapter is very important because in this case, Anchor actually cannot really help you. It can help you to some extent, but actually Anchor doesn't know anything about your logic, about your program. So Anchor can only do what you tell it to do. So the math and logical issues, you have to take care of them by yourself. One of them, or the most common, is of course are the problems with arithmetics and precision issues. So very often it happens that you have some kind of overflow or underflow, so you should always use, or maybe not always, but in most cases you should use the checked arithmetics in Rust, and you should verify your calculations. So yeah, that's why also at the very beginning I told you that it is very important to test extensively your programs, because such kind of issues can be effectively discovered within the tests at the beginning or before the deployment, if you have the tests. Then you should validate the account data and the instruction parameters. So again, Anchor can help you to deserialize the account data, for example. It will help you to check that somebody didn't supply, for example, incorrect accounts with the same structure. Then Rust can help you to verify that the supplied parameters to the instructions have actually correct types, and so on. But Anchor and Rust again do not know what you would like to do with this data and with the values. So it's entirely on yourself to verify that the values that are supplied to your program are correct, and that they are, for example, within the correct range, and so on. The next point here is that you should make sure that the instructions are executed in correct order. So sometimes it might be quite logical that, for example, in the case of a voting program, that you would like to wait for the voting before the voting actually starts. So let's imagine you have some starting date, so of course you would like to receive the votes after the starting dates. So it's kind of logical. For that, common practice is that you keep some kind of internal state in your program, and you just check that your program is in the correct state. In some cases, it might not be so obvious, so there might be different scenarios where you will, for example, set some data in one instruction that will be used then in another instruction. So again, in that case, you have to prevent the bugs by testing, for example, the different order of the instructions. And then the last very common problem that I would like to share with you is that you should also prevent unintended behavior when you pass duplicate mutable accounts, actually, the accounts do not have to be mutable, but very often you want to have, for example, user A and user B, and there is some action that happens, but you don't think about the situation if somebody will supply the same account for the user A and user B. So this is something that you should have in mind, and again, the best thing is to do the proper testing for that. The way how you can prevent it is, for example, using the anchor constraints, and you can have something like this, that the user A key is not equal to the user B key. That way you can keep the check or the security check within the context, and you don't have to mix it with your logic. Next in the line are the reinitialization and revival attacks. So they are kind of related because they are related both to the lifetime of the account. In the first case of reinitialization, it's that you actually, in most cases, don't want to reinitialize an already initialized account because a new initialization might reset, for example, some internal state, and it would give the opportunity to an attacker to exploit your program. To prevent that, in Anchor, it's quite easy, so you can just use the init constraint on an account, and what actually Anchor does is that it adds discriminator to a data account. A discriminator, it is array of 8 bytes at the beginning of the data that are basically related to the data structure that you saved in the data account, and the init constraint actually checks that the discriminant was checked or not, was set or not, and if it has been set previously, then it will not reinitialize the given account. Then the other situation is the revival attack. So it's similar because you actually do not want to reuse an already closed account. To close an account on Solana, you have to set its LAMP port to 0, and therefore the account will not be rent exempt anymore, and it will be garbage collected by the runtime. However, the garbage collection actually runs only after the transaction is finished, and therefore, if the account is not closed properly, an attacker can close an account in one instruction and then include directly a new instruction to reinitialize the account, or he can, for example, send new lamp ports to the account, and that way the account will not be garbage collected. Again, in Anchor you can use the close constraint, and you have to include the receiver account that will receive the rent lamp ports, and the close constraint actually resets or sets the discriminator to a new value that is specific to a closed account, and that way you cannot basically reuse the already closed account. And then I have also included some other issues, so we don't have a lot of time, so we cannot cover all the possible issues within the time frame that we have, but I wanted to mention them anyway, so that you know that it exists. First of them is that you should verify the account data type to avoid so-called type cosplay. It means that an attacker could eventually supply a data with different data type, and then your program would deserialize it with the given data type that does not correspond. And as the data types might overlap, for example, it might still be deserialized correctly, but with incorrect data, and it might give the attacker a possibility to exploit your program. In Anchor, this is very easy. You can only use the account type with your given type, and then Anchor checks the discriminator at the beginning of your data to match the data types. Then the next point is that you should always use the canonical bump to avoid multiple valid PDAs. Canonical bump means that this is the very first value of a bump that you calculate when you calculate the PDA address, because a PDA address, as you might know, it's a special address that is so-called bumped off the curve, and therefore it doesn't have a private key, but there might be different values of the bump. So there is a best practice that only the canonical, so that means the first or the highest bump number should be used to avoid having multiple valid PDAs. And the way how you can do it is that you should basically use Anchor in the standard way, that you will either leave the bump here empty, so therefore Anchor will calculate it for you, and Anchor takes every time the canonical bump. Or you can, as you can see here, you can use the bump that you have stored previously during the initialization. So here the data.bump refers to a bump value that is actually saved in your data account. But you should never let the user to choose an arbitrary bump. And the last point here is that you should not use shared or global PDA authorities. Instead, you should use specific or user-specific PDAs. So here in that example, you can see that you have two accounts, so one data account and the user account. And as you can see here, the data account is related to the user account because the seeds are derived from the user's public key address. So you should never have a global PDA account that gives authority to deal with data from other users. Of course, there might be or there are some use cases, but general practice is to avoid this. And last but not least, I have here for you a recommended resource. It is actually a lesson from Solana itself. Here is the address, soldev.app course, and if you will scroll to the bottom of the page, there is a last module 7 on the program security. I highly recommend you to go through these lessons. It's quite extensive. There are different examples. There are also different demos. It has been inspired by the examples from Armani, who developed Anchor. So I can highly recommend it if you are interested in more details. So that's it for the common exploits. Maybe at the very end, I would like to do a short wrap up. Again, I have repeated here the tips that I showed you at the very beginning, that I recommend you to use Anchor, and its built-in security features. It has really nice advantages, as I explained before. You should test extensively your programs and have your project audited. As I said before, so everybody makes mistakes, and it is again usual practice to audit your projects. And maybe some other tips: that you should avoid non-standard code and libraries. So I believe that if you will follow the common practice, and that if you will follow the guidelines from Anchor, then you can avoid a lot of bugs that are Solana specific, and then you can actually focus on the logic and test the logic of your program. Another tip is that you should compare the list of common exploits with your program regularly. So it's very easy to forget about something, or very often you modify multiple times your program. So maybe at the very beginning you thought about different scenarios, but after some modifications you integrated some bug without knowing it. So I recommend you to go quite often through the list of common exploits and compare it with your program. And the very last point is that I have shown you different possibilities of exploits, but very often in practice the exploits might be a combination of multiple issues that you have. So it doesn't have to be only one of them, but because you actually have two different issues it might give the possibility to the exploiter to with your funds, for example, or something like that. So as a separate issues, maybe it is not critical, but you should all the time consider more complex scenarios. Yeah, so that's it for today. I hope that you have learned something, and thank you very much, and see you next time.